Okay, I wanted to go through a question from the homework that has to do with a quadratic sequence. So I want to kind of remind you a little bit. We've already talked about linear. Remember linear patterns that like add or subtract the same number each time. So they'll have the same first difference. And they've also talked about exponential, which are numbers that multiply by the same number. In the other notes we saw, and we kind of got this idea that there is a quadratic. There's this new type of pattern that we're going to learn this year, whereas these two, the linear and exponential, you should have learned last year. So quadratic's this new one, but I don't think we quite went through an example where we actually wrote the equations of it. So I thought this will help you, particularly if you look at your homework. This goes along, I believe, the question 6 on there. If not 6, it should be one kind of in that range, and hopefully it helps out. Okay, consider the tables and the value below. You're welcome to leave it that way. I personally just kind of like it a little bit better when it's horizontal. So I can leave it still as f and f of x, but I'm just going to rewrite these numbers 1, 2, 3, 4, 5. And I've got my y values of 2, 5, 10, 17, 26. So that's just the numbers in the table, but I like this format better. As I look at these numbers, I would just ask yourself, like, hey, am I multiplying? Like 2 times something is 5, that's a fraction. 5 times 2 is 10, but like that pattern doesn't continue. It's not like I'm multiplying by 2 every time. So in which case, we're going to look at what we're adding each time. So I'm going to kind of make this table a little neater. Let's see if I can do this. So think about it this way. To get from 2 to 5, I am adding 3. To get from 5 to 10, I am adding 5. From 10 to 17, I'm adding 7. And 17 to 26, I'm adding 9. So notice we do not have the same first difference. So it helps if it's linear, it will have the same first difference, and that's not the case. In this case, this pattern is a linear pattern, so we've got something linear going on up here for the first difference. So let's look at then with a quadratic, we're going to have the same second difference. So if I look to get from 3 to 5, I'm adding 2. 5 to 7, I'm adding 2. 7 to 9, I'm adding 2. So because it has the same second difference, it makes it quadratic. So as we look at these options for this one, which statement best describes the characteristics? The rate at which the value increase is not constant. That's true. The first difference is not constant. The first differences are linear. The blue part's linear, right? That was true here. And then the second difference is a constant too. Okay, so this would be my answer there. This is telling you the first difference is the constant too, which that's not the case. It's the second difference, right? So that doesn't work. The next one says it's a multiple of 2, and the last one says none of these do it. So we know if it's the same second difference, it's quadratic, right? Okay, so that helps you maybe put that here, like same second difference will always make it quadratic. Okay, whenever we're writing an equation, I think it helps to kind of have a formula that you can follow. So I'm going to start actually on part D because I think the recursive is slightly easier than the explicit. Okay, there will always be 2 parts to the equation for recursive. So the recursive will always be f of 1 equals a number. And notice this is usually given to you. So like, hey, in our problem, they tell you that f of 1 equals 2. They will also tell you that f of x equals f of x minus 1. To put this in layman's terms, it's saying to find the next term, you take the previous term, and we're going to add something. So if you look up here, like starting at the first term, we're going to take 2, and we added 3 to get to 5. To find the third term, you take 5, you add 5 to get to 10. To find the fourth term, you take 10, you add 7 to get to 17. That's what they're saying when they're saying, okay, we take to find the next term, we take the previous term, we're adding that purple column. So in our case, I'm just going to call it the purple column. I guess maybe I'll just say like the linear function. Not the purple, sorry, that was actually the blue column. So the linear pattern, which is like the blue column. So the trick here is to figure out how to write that linear pattern. I think when we see linear, most of us are used to like mx plus b. So that's the format I'm going to use. So we're going to have f of x. Okay, so now let's actually go back and let's start writing an equation. So to write our equation, we're going to have f of x equals f of x minus 1. Right, to find the next term, we take the previous term, plus we're going to fill in some slope, x, plus some b, which is your y-intercept. So let's go through and let's figure out what these values are. This m is going to be your second difference. So the slope here, right? The slope of that blue linear pattern is 2. Okay, b now is known as your like y-intercept, right? So this is like your y-intercept. Which in our case, the y-intercept of the blue column, we can think about it as like the 0 term of the first difference. So it's saying, okay, if I keep going back here, I want to do the 0 term. So when x is 0 of that blue column. So think about it, we're adding 2 each time. So if I go backwards, I'm going to subtract 2. So 3 minus 2 is 1. 1 minus 2 is a negative 1. So in our case, this would be like a negative 1 at the end. You can write it like that, or you can just do it as, let's see if I can erase this a little bit, just like what it looks like there, 2x minus 1, which I think is a little bit neater than the plus the negative 1, but either way does work. Okay, that will be like the same format every time for recursive. So you're kind of finding out that mx plus b that you're adding. Let's talk about the explicit one then. I'm actually going to come down here to like the bottom a little bit. So explicit equations will follow the format f of x equals ax squared plus bx plus c. Okay, there's always some patterns that they follow. The a will always be the second difference and then divided by 2. All right, maybe I should kind of start writing this up here. So our equation will be like f of x equals something x squared plus maybe something x plus something for the c. So you're replacing, I guess this is a good thing to point out too. Let me highlight it for you. You're only replacing, so in this case, like, you're going to replace the m. Ooh, what is going on? Sorry, give me 1 second. Let me see. Oh, that's that. Let me do this. I gotcha. Sorry, technical difficulty for a moment there. We're going to replace the m here and the b. In the explicit one, you're going to replace the a, the b, and the c. I'll talk about that some more. So in this case, if we take our a term, which is 2, and we divide it by 2, we would get that a is 1. Because this comes from like 2 divided by 2. Okay. The c term, let me look at purple column. Okay, so it's in purple, is going to be like the y-intercept of your quadratic. So it's going to be the 0 term of f of x, or like your y. So once again, I need to kind of go back and figure out what's going to be there. So you're really saying something plus 1 is equal to 2, which in this case would be 1. 1 plus 1 is equal to 2. So plus 1 at the end. Okay, I'm going to go through the process on this one, but I'm going to tell you right now, in general, on these ones, we're really only focusing on the first or last term, so you're not going to have to worry about bx, so you can have it disappear, but as we continue on this unit, you may need it, so let me kind of discuss about how you find this. In this case, plug in an xy, and solve for b. So let me show you in this case what I mean. So if we've got our equation over here, like example, we've got f of x equals 1x squared plus bx plus 1. Choose another point. It could be any point on there, but I'm going to choose the point 1, 2 because it's kind of the smallest numbers, and I think smaller numbers are easier to deal with. So we're saying our y value is 2 and our x value is 1. 1 times x squared for the record is just x squared, so we don't really need that one. So we're plugging 1 in for x. We got 1x squared. So I'm going to use the point 1, 2 plus b times 1 plus 1. So 2 equals 1 squared is 1 plus b times 1 is b plus 1. So 2 equals 1 plus 1 is 2, 2 plus b. Subtract 2 from both sides. Do you see how b is 0? So you could totally in this equation write that b is 0, but there's really no reason to have that. And I think it's probably a little bit cleaner just to write that f of x equals x squared plus 1. Okay, the last but not least step of this one is on the homework. It will have you take these points. You simply just drag it, so you kind of drag this up and then plot it at like 1, 2. And it's nice because it tells you where you're like landing. This next one's going to be at 2, 5, so you just drag that point up and then plot it at 2, 5. And you keep going. So then the next one, 3, 10, you drag it up, you leave it at 10. Then we have 4, 17. Keep dragging it, and then it should go kind of around here for 4, 17. And last but not least, 5 and then 26. So I think that's just a little bit above what you can see right now in the graph. And you're all done. Let me know if you've got any questions. Hope this helps.